This presentation outlines the results of research focused on the design of energy-aware control system, reducing power consumption cost of quality of service provisioning in an experimental network of Linux software routers. The developed control system automatically adjusts performance of the network to the workload generated by the network traffic. The obtained results of experiments show that in the addressed environment, the control system allows to reduce power consumption by 20% if traffic rerouting, hibernation of nodes, and local router performance control mechanisms are used. If only router performance control mechanisms are active, the system allows to reduce power consumption by 5%. In each case, the reduction of power consumption is achieved without deterioration in the quality of service. Development of the control system was concentrated on the design of local control mechanisms, network-wide control mechanisms, and workload forecasting and monitoring tools. The local control mechanisms were designed to adjust individual performance of each router in the network. The network-wide control mechanisms were designed to coordinate interactions of the energy-aware routers by scheduling activity of the network devices and optimizing routing tables. Finally, traffic workload forecasting mechanisms and network monitoring tools were designed to support operations of the control mechanisms. A two-layer control structure was developed. The structure consists of a network control and monitoring layer, operating at the level of network manager, and a local control and monitoring layer, operating at the level of network devices. The upper control layer is responsible for periodical optimization of energy-aware routing and energy-saving configuration of the network. The lower layer executes commands received from the upper layer, collects measurements, and controls routing performance. The local control and monitoring layer has a direct access to each router in the network and is in charge of executing basic control commands. In the developed environment, it is responsible for energy-aware CPU frequency control, router suspending and activating. It is also responsible for collecting measurements of routing performance and power consumption. Each router in the constructed experimental network was equipped with 1 gigabit network interface card and CPU capable of operating at 16 frequencies. Each router was also connected to the power consumption monitoring system. In order to control traffic flows in the network, a port policy-based source routing mechanism was implemented. In addition, each router was equipped with a TCP dump-based probe performing real-time packet inspection. Both mechanisms, when activated, generate CPU workload correlated to the amount of traffic forwarded by a router. Consequently, two types of nodes were distinguished in the network: packet analyzing nodes and packet forwarding nodes. Each type was subject to the performance profile identification procedure. As a result of the system profiling, a collection of best response functions was constructed, each function corresponding to a fixed value of weight assigned to the power consumption cost. A best response function determines CPU frequency at which an observed workload is served at minimal cost. The required CPU frequency control policy was designed based on an approximate solution to the multi-objective stochastic optimal control problem. Formal analysis of the problem shows that an efficient control policy can be defined by a router's best response function and efficiently implemented as a lookup table. The network-wide control layer monitors performance of the network and adjusts its energy-saving configuration. Graphical user interface of the layer illustrates measurements of the collected data, in particular, active topology of the network, total power consumption, and CPU load of each router. Based on the collected measurements, the upper control layer generates peak workload forecasts for each registered stream in the network. These forecasts, together with the identified performance profiles of the routers, are used to optimize routing tables and to set up activity levels of the nodes. In order to calculate routing tables and energy-saving configuration of the network, a constraint optimization problem is solved. As an input, the problem solver receives the power consumption profiles and the peak workload forecasts of traffic flows. As an output, the optimization procedure returns a description of energy-efficient routing paths capable of forwarding the forecasted amount of traffic. Based on the obtained solution, the routing tables are next generated together with the required configuration of the network. In the period between the subsequent calls of the routing optimization procedure, the upper control layer performs a regulatory control of the operations performed by the lower control layer. The goal of the regulation is to maintain the quality of service constraints along the activated routing paths. Performance of the developed system was tested experimentally. The main goal of the experiments was to estimate the expected performance bounds for energy-aware networking in the Linux-based environment built of the commercial off-the-shelf components. The following video presents performance of the system. Whenever traffic workload is forecasted to be high, additional network resources are activated. In order to keep the required quality of service level, some of the connections are redirected to new routing paths. Reconfiguration of the network is commanded by the network-wide control layer and executed by local control layer. Whenever traffic intensity is forecasted to be low, the system automatically reduces activity levels of the routers. As a result, the traffic flows are redirected to the optimized routing paths. The obtained results of experiments are summarized in the following final figures. The first one illustrates measured performance of 5 CPU frequency control strategies. To obtain a comparison of outcomes, the average performance of each control strategy was divided by the worst case average performance. The obtained ratios are represented in the form of bar charts. The results show that in the addressed environment, the applied CPU performance control mechanisms were able to reduce power consumption by 5% without quality of service deterioration. Better outcomes were obtained when traffic rerouting and hibernation of nodes were applied. The second figure presents a comparison of 3 network-wide control strategies. In this case, the system was able to reduce power consumption by 20%, keeping the quality of service at high level. For more information about the research on energy-aware networking, visit the ECOnet project webpage.